Thank you so much for the invitation to be here. I'm glad I could come in person. My name is Carolyn Kierans. I'm a research scientist at NASA Goddard, so over in Greenbelt, Maryland, pretty local. And I'm going to talk to you about something that is very different than your expertise, maybe, for most of you, is developing next generation gamma ray telescopes. These look very different than what you guys have been talking about in terms of telescopes for the past little bit. And I'll try to introduce you to that concept of what they look like in the instrumentation side, but also motivate it scientifically. I'll also describe the image that you've been looking at for the past, I guess, 20 minutes now. So this is a photo I took just on my iPhone, but this is actually one of my favorite photos that I took from a balloon campaign in Fort Sumner, New Mexico in 2023. On the bottom left, right there, you see actually the Compare 1 telescope, which I'll introduce you to today. That gondola that is hanging beneath the crane is bigger than me, just to put that into scale. Over on the left are two semi-trucks pulling compressed helium gas. So these are massive trucks that are about to be inflating a very large scientific balloon. And then the amazing thing about this image is, you probably already saw it, but the Orion constellation is in the top right. And the Orion constellation is near and dear to my heart because this is what first got me interested in space science. Looking at the Orion Nebula in a backyard telescope when I was 12 or so, it just really blew my mind. And I'm sure you guys are all much more familiar with that than I am. But the fact that I was able to capture this in all of one photo with my iPhone makes this one of my favorite, bringing it all together. Okay, so today I will first introduce you to the gamma ray sky, what we see when we look at our galaxy and beyond in the gamma ray energy range. I'll talk about using gamma rays as a tool to study astronomy and astrophysics. And then I'll spend time talking about technology development, why we need to develop next generation gamma ray telescopes, how to build a gamma ray telescope, what it looks like. And I'm going to talk about the Compare project, which I'm the principal investigator of at NASA Goddard, where we're testing technologies for a next generation gamma ray mission. And we're doing that on scientific balloons. Okay. So to get everyone on the same page, when we talk about gamma rays, what are they? This is a picture of the electromagnetic spectrum. So most of what you guys do when you look at stars is in the visible regime. So that's in the rainbow colors. We have lower energies, for example, or at longer wavelengths. This is the radio regime. You're also familiar with UV emission coming from the sun. Higher energies than UV is X-rays. So this is where photons actually turn into penetrating particles. They can make it through our skin, but not make it through the dense bones, and so you can actually make images of bones. Higher energies than that is gamma rays. So you often will hear about this when we talk about radioactivity, right? The Hulk was created from gamma rays. That is one aspect of it, but gamma rays is basically anything higher energy than X-rays. And this is a huge energy regime. There is no upper limit here. This is billions of times more energetic than the photons that are coming from the sun. And this is the regime that I work in for studying space. How we do astronomy or how we do astrophysics is very dependent on the wavelength that we're looking at. And that's not only based on the detectors that we're making, but also how those wavelengths make it through our atmosphere. So what this is depicting is the absorption probability or transmission probability, excuse me, through the atmosphere. So we can do ground-based astronomy in our backyards because visible wavelengths make it to Earth. Right? They make it through the atmosphere. They do not get absorbed. The same is true in the microwave and the radio. So that means we can do ground-based astronomy in the microwave radio regime and in the visible. The same is also true at the highest energy of the gamma rays, but I'm not going to talk about that today. For everything else, we need to go into space to actually observe outside of our own atmosphere, looking at the stars. And the science that we can do is dependent on the satellites that are then in orbit. And so NASA's astrophysical fleet is what I'm bringing up here. This is shown as a function of energy and also as a function of the launch date. So the longest operating mission that NASA has launched is Hubble. You guys are probably all familiar with the amazing stars and pictures that Hubble has produced. So it was launched in 1990. I might get the year wrong, plus or minus 1 or 2 years, in 1990. And the most recently launched from NASA is the SPHEREX mission, which is also operating in the infrared regime. There is a huge cluster of X-ray missions, and there is one operating NASA gamma ray mission called Fermi. And that's it. And importantly, there is nothing between the what we call KeV energy. So actually, let me describe the energy scale before I start using these terms. In the gamma ray regime, we talk about the energy of a particle in the units of eV. So energies or photons or light coming from the sun is about 1 eV of energy, just to put it in perspective. We talk about keV, so that's kilo electron volt, 1,000 times more energetic than photons from the sun. MeV, mega electron volt, or 1,000,000 times more energetic than the sun, and even up to a GeV, a giga electron volt, 1,000,000,000 times more energetic than the sun. So I'm going to use MeV and GeV as a term for gamma rays, as an energy term for gamma rays. So the Fermi emission operates in the GeV range, 1,000,000,000 times more energetic than the sun wavelength range. But there's nothing in between the X-ray missions that are currently operating and Fermi. There is a gap in our observations. And that is where I do my science. Unfortunately, we don't have any observations there, but I'll get into why we need to. Okay, why do we actually care about looking at all these different wavelengths? The science that we can do is limited by the data that we can get. If we want to understand our astrophysical objects, we need as much data as possible. So this is looking at one galaxy, the Whirlpool Galaxy, or M51, in multiple different wavelengths. So at the lowest energies of the radio, all the way on the left, when we look at radio emission from the Whirlpool Galaxy, this is showing us cold regions. This is showing us gaseous cold regions where we actually see molecular clouds. So that's the bright spots, for example, in green. Looking at the center, this is the optical regime. This is what you guys can make with your backyard telescopes, and you have really, really nice ones. And we're seeing emission from optical light from stars that are like our sun. That's very much what we see in the optical regime. At the higher energies, so this is an X-ray image of the same galaxy. You only see bright spots that are consistent with the center of the galaxy. So this is where a massive black hole is at the center of the galaxy, with it basically eating up stars and creating a lot of high energy gas. And then you also actually see a bright spot on the top here. And that's because this galaxy is actually undergoing a galaxy merger. So there's another small galaxy. You can see it in the optical image at the very top. But because it's super energetic, it's emitting very high energy light. So that's what we see in the X-ray. And so to make a complete picture of astrophysical objects, you need to put all of this information together. You need the gamma rays as well as the infrared or ultraviolet or optical to understand everything completely. So where do gamma rays actually come from when we talk about gamma ray emission from astrophysical objects? They're created in the most extreme environments. So massive star explosions, you guys are familiar with supernova, at least the concept of supernova. Also very hot regions of the galaxy, so star-forming regions, jets from massive black holes in the center of galaxies, strong gravitational fields or strong magnetic fields. Basically think of anything extreme and you're going to be creating gamma rays through it. Gamma rays are incredibly powerful tools. So because they have high energy, they can travel very long distances without being absorbed or deviated. In some wavelengths, when you look into our own galaxy, the galactic center is dark, right? The light is being absorbed or blocked by dust in the galaxy. You can't actually see into the center of our galaxies. However, in the gamma rays, they'll blow straight through all that. So you can probe further into objects than other wavelengths. And importantly, gamma rays actually provide a very unique tool to understand the creation and destruction of matter in our galaxy. And I'm going to talk about how we can use them uniquely as a tool to understand how elements are formed, because this is why I'm particularly interested in gamma ray astronomy. So you guys have probably all heard the famous quote, "You are made of star stuff." What that means is that the life cycles of stars, the evolution of stars and the deaths of stars are responsible for all of the elements in our visible universe. Everything we see and around us is created in stars, at least since the Big Bang. And that happens kind of in two main processes. The first is through what we call stellar nucleosynthesis. So nucleosynthesis is the synthesis of nuclei or the creation of elements. And that happens just as a regular star grows and evolves. So you start with hydrogen and helium in a core, the star fuses new elements, and you create this onion-like structure, building heavier and heavier elements in the star's core. This doesn't perfectly match an onion structure, but that's the cartoon picture of what we understand as stellar nucleosynthesis. At the end of the star's life, if it is massive enough, it will undergo a supernova. And this is where we generate explosive nucleosynthesis, or what we say is the explosion energy produces new elements, and those heavy elements are then released into the interstellar medium, or released into our galaxy. Outside of the interiors of the star, it is then released and it can be recycled into new stars or new planets or eventually life. So I'm going to show this picture on the right a few different times. This is a supernova remnant Cas. It is actually a full image, not just an artistic impression. I mean, you guys see these beautiful images all the time, so you're not surprised by how beautiful this is. But what you're effectively seeing is the shock waves of matter interacting with the surrounding medium after a supernova has happened in the center. So another way to see this is by looking at the periodic table of elements. Here, the periodic table is color-coded based on the astrophysical origin of that element in particular. So from the Big Bang, we get hydrogen, helium, and a little bit of lithium, so that's colored red. We have exploding massive stars, so supernova is creating all the elements in blue. And then in yellow, the heaviest elements are predominantly coming from merging neutron stars. So neutron stars are these very exotic, very hot, heavy stars that are created after a supernova goes down, and you have a merger of them, you get very dynamic environment, which creates the heaviest of nuclei. What's important to realize is every time one of these elements is created in these very extreme environments, it's created in a stable and a radioactive form. So when an element is created radioactively, it needs to decay to stability. Things don't like to be unstable. They will decay to a stable element. And when it decays, it emits particles, and it always is going to emit a characteristic gamma ray. This gamma ray energy points us back to the isotope that decays. So the gamma rays from nuclear line emissions, so the gamma rays from nuclear decays can act like a fingerprint-like probe of the isotope that decayed. So if I see a 1.8 MeV gamma ray, I know that came from aluminum-26. So I memorized that one. There's tables that you can look up so you can match between different energies and different isotope decays. But this is a very particular tool that we can use. If we look at our sky, if we look at our galaxy and we measure a very specific energy, we know what isotope that came from in particular. So this is what we call using gamma ray or gamma ray line astronomy. We use gamma ray lines to do astrophysical studies. Unfortunately, we haven't seen many of these before. So these are all of the isotopes or the elements that we've measured gamma ray line signatures of outside of our own solar system. And I'm going to talk about a few of these in particular, because this is just the tip of the iceberg of the science that we can do. This is very much still in its infancy. Only 2 telescopes have ever done this before, and we're trying to build more to continue this science. So I'll talk about the science we can do and then motivate the need to do more. So looking at 2 particular isotopes, the first is titanium-44. So this isotope of titanium is created, it's a heavy element, right? You guys are familiar with titanium being a heavy metal. It's created in supernova explosions, and it's really unique because it's actually created right at the boundary of what falls into the collapsing star, forming a black hole or neutron star, and what gets pushed out. And it's very sensitive to the energy or the temperature or the mixing of the supernova explosion. So if we know there was a supernova somewhere, and we measure that amount of titanium-44, the theorists can go back and check their models, and they're like, well, we expected this much titanium. So then they have to fudge their models and make it work out. So it's a really useful metric of supernova models. Only been detected in 2 supernovas so far. So it actually decays, emits 2 characteristic gamma rays, 68 and 78 keV. And the New Star X-ray mission, which was launched by NASA in 2011, I believe, is sensitive to these energies, specifically the 68 and 78 lines. So they can measure these very specific gamma rays, 68 and 78 keV, and they know they're measuring titanium-44 decay. So I'm going to walk through this plot just a little bit slow, but this is actually like a science paper that is showing the measurement of titanium-44 from the Cas supernova remnant. So this plot shows the measured spectrum, what we call kind of the energy distribution of the supernova, and it's really long and flat. This is what we call power law spectrum. It follows an exponential decay, kind of what you expect from something that is has exploded. This is supernova. And then these 2 blips at the end that you can see in orange. That is the 68 and 78 keV energy line. And those blips, once we saw them, we know that's titanium-44 decay. This insert here is just a zoom in of those 2 blips on a slightly different scale. And what they actually do, and I don't need to go too far into it, but it is really interesting, is they've plotted the true energy that they expect in pink. And you can see the peak is actually shifted. So these lines are red shifted because the emission is moving towards us. So they're actually Doppler shifted effectively. And so you can actually use these measurements to figure out how fast this ejecta is moving. not only how much there is, which tells us what the supernova energetics were, also how fast it's moving. So you can see now, whatever it's been 350 years later after this explosion, what the projection is looking like. So it's an extremely powerful tool, but we've done it twice. So measuring titanium-44 from supernova, specifically these gamma ray lines, is the most direct way to constrain supernova explosion models. The nuclear theorists love this, and they want us to develop more measurements so that they can use that to key in their models. So that's titanium-44. There's another gamma ray isotope that I kind of want to spend a bit of time talking about, and that's aluminum-26. So aluminum-26 is actually the poster child of gamma ray line astronomy. It's really unique because this aluminum isotope actually has a 1,000,000-year half-life, which means when it's created, it takes 1,000,000 years before it decays to a different isotope. And this is creating that 1.8 MeV characteristic gamma ray that I've already mentioned. But when supernovas, they only go off about once per century in our galaxy. And with a 1,000,000-year half-life, that means the aluminum-26 is built up over tens of thousands of supernovas in our galaxy. And all the aluminum from all those different supernovas is basically clumping together and creating a diffuse glow in our galaxy. So when we try to image that very specific 1.8 MeV gamma ray line, this is what telescopes saw, at least in the 90s. So this is a little blurry. It's low resolution, not great sensitivity, but this is an image of our galaxy. So the center of the galaxy is in the center of all my images. I don't know if I have any other galactic images, but I do everything in galactic coordinates. So the center of the Milky Way is in the center of the galaxy, and the Milky Way plane goes along the lateral here. So those hot spots correspond to the spaces where we have the most 1.8 MeV emission, so the most aluminum-26 from these previous supernovas. And the clumpiness kind of is consistent with what we know as our star-forming region, so basically our spiral arms of the Milky Way. But the image kind of sucks. I'm not going to lie. This is the best that has ever been done in this energy range. The clumpiness is mostly limited by the angular resolution. You see a lot of structure kind of at the top and the bottom. This is mostly imaging artifacts because imaging in this energy range is really challenging. It's just not making a picture. And I'll describe that a little bit more. This is the best we've been able to do, but measuring the aluminum-26 tells us about how massive stars that either undergo supernova or actually just diffuse their isotopes into the interstellar medium, how they are going about creating elements by looking at these specific gamma ray lines. We just haven't been able to do it very much because we're very limited by our technology. So another way to see this limitation is by looking at the continuum sensitivity of telescopes, both previously operating missions and currently operating missions, as a function of energy. So the y-axis here is the sensitivity of the telescope. Lower numbers means you can see fainter objects or you can see further out. And this energy axis shows X-rays, medium energy gamma rays, and those high energy gamma rays. So this is MEV and GeV along this axis. And what you'll notice is the telescopes that have been previously operating, none of them are operating anymore, but the telescopes that have been previously operating in this gap region, they're orders of magnitude less sensitive than the X-ray and the high energy gamma ray regime. This is what we refer to in gamma ray astronomy as the MEV gap. This is a gap in sensitivity where we have underexplored this region of our cosmos, but we know there's really interesting science. And particularly, sorry for this, I don't know what that blue line is doing, but particularly this is where the nuclear gamma rays are. So it's not that there's not interesting things to see there, it's just that the technology has been challenging. Fortunately for us, there's actually going to be a mission launched next year called COSY, and COSY has been designed specifically to study these nuclear gamma ray lines. I'm going to talk about COSY a few more times throughout this presentation because I use the COSY development as kind of a guide for how I'm developing my telescopes now. I did my PhD work on the COSY when it was a balloon, on the COSY mission when it was a balloon mission before it got selected to be a satellite mission. And I still do a lot of work on COSY, so feel free to ask me questions about it later, but that is not the purpose of the talk. But it was designed and developed really to probe this energy range, but you can see it's just, it's gonna do a little bit, right? It's not gonna fill this gap. So the data provided by COSY starting next year is going to be amazing, but we need something that really fills this gap to really push these sensitivities down to see not only our galaxy better, but the next galaxies. We can't even see Andromeda, nuclear lines from Andromeda, right? You can see that with your naked eye, but we can't do that even with the most impressive telescopes that we have in the gamma ray regime yet. So that's what we're pushing towards. So what does a gamma ray telescope look like? So how do we go about building one of these? Gamma rays are penetrating forms of electromagnetic radiation. If you put one of your telescopes in front of gamma rays, they're going to go straight through that thing. A mirror lens is not going to be able to focus them, unfortunately. And these high energy gamma rays, they start actually acting like particles instead of waves. So we effectively need to build particle detectors and put those into space. We have large, and I mean large, detectors that are sensitive to the interactions of gamma rays as they bounce through our detector material. And I'll talk about two different ways in which we actually look at these gamma rays and how they can trace through the detector material for us to actually do this imaging. You can zone out while I'm talking about this plot if you want, and I'll tell you about the takeaways, but I will get into the kind of the physics of what's happening within these detector systems. What this is actually showing is the probability of a photon interacting with matter as a function of energy. So at lower energies, a photon is predominantly going to interact with photoelectric absorption, which I'm actually not going to talk about, so I shouldn't have even said that. Once we get up to MeV energy ranges, the dominant photon and matter interaction process is called Compton scattering. A photon actually interacts with an electron around an atomic shell, imparts some of its energy to that electron, and moves off at a lower energy. So it is like a billiard ball. That photon is scattering off an electron and moving off at a lower energy. So if that's the predominant mechanism in which a photon is interacting with matter, we have to take advantage of that in our detector systems. So we built telescopes that are called Compton telescopes that take advantage of Compton scattering. So a photon will enter our detector material. It will scatter 1, 2, 3, 5, 10 times before it ends and deposits all of its energy in our large detector material. And we need to measure the position and the energy of each of those interactions to figure out where that initial photon came from. We can't measure that photon until it interacts. So this photon path is only drawn on here because we figured out where it actually went. We have those 3 data points. But we have no sensitivity to that photon transferring until it actually scatters. So this is called the Compton telescope. And this is how the previous mission CompTel worked. So that aluminum 26 emission, that was done by a Compton imager. And this is how COSI's upcoming mission in 2027 is going to work as well. So it's a large detector material with very precise position and energy measurements within that detector material. At slightly higher energies, once we get about 10 MeV, the dominant interaction process is pair production. So your photon is going to interact around an atom and actually convert from a light particle to 2 particles, to an electron and an anti-electron, a positron. And then 2 particles come out of that photon conversion. And so we build our detector systems such that if a photon converts into an electron and positron pair in our detector, we can track those charged particles within our detector. So again, we need position-sensitive detectors. We need very large detectors to stop these energies. And we're able to determine where that photon actually came from to do our imaging. This is how the Fermi Large Area Telescope does its imaging. So that one operating mission that's still going, this is what that detector system looks like. Okay, so that's generally what gamma ray detectors look like. They're big, they're dense, they're heavy, and we're measuring particle interactions effectively in our detector system. And we do some kind of calculus to kind of work backwards to figure out where each individual photon came from. But it is single photon imaging. Yes, please.
How do you determine the angular resolution of your telescope?
So, great question. You build up, so for Compton scattering, it's a little bit different. So you can actually only determine the individual projection of each photon to a ring in the sky. You can calculate this initial Compton scattering angle of this interaction. And so you can constrain a photon, you can say, I know it came from somewhere on this ring. But individual photons will then, from the same source, your rings will overlap. And you'll slowly build up an image. I had a GIF, I got rid of it, but you'll slowly build up a bright spot where all those rings overlap, and that's where your source is. So if you can do simulations or you do measurements in the lab and you see how accurately all of these rings point to where your actual source is, that is what your angular resolution is. So in the gamma ray regime, and I wasn't going to go into this, but I'm happy to talk more about it, our angular resolution is on the level of degrees. The moon is half a degree, right? When you hold your thumb at arm's length, that's about half a degree, about the size of the moon. We can tell a gamma ray came from like my hand region in the sky, and that's considered good. There isn't anything better. We're limited by physics, actually. And yeah, I'd be happy to talk more about why we're limited by to the level of degrees, but we're currently limited to degrees. In the pair regime, you can do a little bit better. You can get half degree, maybe 0.2 degrees at higher energies, but it's still on the order of degrees.
So that R3E3 would produce a cone in the star.
Yeah.
So, but it wouldn't be that cone. It would be
So this is a single photon going through and scattering multiple times. And every photon, you look at the first two interactions of a single photon in your detector. And those first two interactions allow you to back project kind of this axis. And this Compton scattering angle tells you the radius of this circle. So from one photon interaction, you get a circle on the sky. From another photon interaction, which is going to look very different in the way it scatters in the detector, you're going to get a different ring on the sky, which might be a small ring or a really, really big ring, but it should overlap at the gamma ray source.
Is it possible to do, if you had 3 X-ray telescopes, can you do triangulation? If they're at different, if you have a.
So you can, so the good thing for right now is we're not limited, we're not confused about which source we're looking at.
Okay.
We're not yet at the point where we have the sensitivity enough to have trouble distinguishing between sources in the galaxy. So there's basically 40 or so sources that have been detected in the MEV range, and we know exactly what they are corresponding to X-ray images and higher energy images, and that's just the brightest that there is.
Yeah.
After the next generation telescope gets launched, we're going to probably be at that limit where we're going to have to start being really careful about how we associate large globes in the sky and what source is associated with that. But triangulation is not going to help you, unfortunately.
So you have scopes now that when you get a gamma ray burst, a signal goes out, and then observatories with X-ray telescopes can immediately go.
Yep, for transient objects, for things that go boom in the night, we can figure out where those came from because other people will follow those out.
Right.
But for things that are just shining persistently, we'll have to figure out either maybe the spectrum we can extrapolate from lower energies or higher energies. Soon we'll have that problem. We're not there yet. We don't have enough sources to be source confused. Yeah. But the angular resolution in the gamma ray regime is a very big challenge that we're unfortunately like physically limited from exploring. Ask me about focusing optics in the gamma rays later, and I'll be happy to talk here your own. Okay, so now that we kind of know what a gamma ray telescope looks like, and I know this is just skimming the surface of things, but just to get you in the mindset, how do we go about actually getting NASA to give us hundreds of millions of dollars to build one of these? So we're going to look at the upcoming COSY mission as an example, because that's what I tried to base my research on. So COSY started with a new technology, and it was actually in 2000. So my PhD thesis advisor back in the day found these detectors that people were working with, and he realized that these would make really good next generation gamma ray telescopes. So we started doing some tests in the lab. It took a couple years to get development, but things really take a kick when you actually show that a prototype instrument works in a space-like environment, right? Showing that it works in the lab is only going to get you so far. You really need to show that it actually works in space. So this is where the NASA balloon program comes in. And I'm going to take a bit of a detour to talk to you about the NASA balloon program before going back and finishing the COSY story. How many of you have heard of NASA scientific balloons before? Oh, actually, wow. Okay, so maybe I don't have to sell this so hard, but I'm going to at least give you my spiel, because I am a huge fan. I do not work for the NASA Scientific Balloon Program. I am just a user of it, but I am a huge fan of the NASA Scientific Balloon because it is a unique platform to not only do some science investigations, but it's unique for technology development, especially in the gamma ray regime. And so the plot on the bottom is actually an inverse energy order. I apologize from all these other plots. I've been thinking about remaking this and I never have, but so we have radio at the lowest energies. It shows you the ground-based observatories. This is showing the transmission through the atmosphere. in the gamma ray regime, they actually show you a balloon, which is why I love this image so much, because it's selling the fact that you need to do gamma ray astrophysics from a balloon platform, or at least you can, because gamma rays at least make it through the upper atmosphere to about where these balloons float at about 33 kilometers up, so 3 times the altitude of airplanes. So the NASA program provides free access for scientists, rides on these very large balloons. So these balloons are the size of a football field in diameter. They can take up multiple tons of weight to 3 times the altitude of airplanes, which is 99.5% above the majority of the atmosphere. The accepted risk of this NASA balloon program allows for rapid development. You don't need some NASA certified person to solder your flight computer together. You can get your grad students to do it. So there's a lot of student labor, which is amazing because it's a training ground, but it also means you can do things very quickly. You can duct tape something on at the last minute before you fly it. And it's about 5 years from your initial idea to getting an initial flight. And this is validating technologies for future gamma ray missions or future satellite missions in general. And I already mentioned that the hands-on training for next generation scientists is really key and is actually one of the main goals of the NASA balloon program, is teaching people how to build something for space. So NASA has multiple launch locations, and I'll mention some of these later in the talk, but Fort Sumner, New Mexico is the main continental launch location. So you do 6 hours to 12-hour balloon launches out of there. So 6 hours to 12 hours at float altitudes. They also have Antarctica as one of the main locations that they do launches where you can stay upwards of weeks or even months. And then finally, Wanaka, New Zealand is where they're trying to push for over 50 to 100 days at float altitudes for science observations. Okay, back to COSY. So COSY had its first engineering balloon flight in 2005. This is much before I hadn't even graduated from high school at this point. I was not involved in any of these things, but the NASA balloon program allows for iterative improvements. You get the hardware back. So you build upon it, you build new, you improve upon it. Sometimes there's launch mishaps. We're not going to talk about that, but feel free to ask me about when things go wrong in the ballooning program. I started my PhD in 2012 with this group, and we were just rebuilding COSY to be bigger and better. We had a launch from Antarctica in 2014, which didn't go according to plan, but we finally had a very successful balloon launch in 2016 from Wanaka, New Zealand, in which we actually got to do some science. So this is what I wrote my thesis on. This is a plot, but it shows the gamma ray line. I'm not going to go into it, but the important thing is that this was the science that COSY was built to do, and we showed it from a balloon platform. Once NASA can see that you're actually doing what you claim to do, we got selected for a NASA satellite mission just a few years later.
That's a care production.
That's 511 line, yes.
Yeah.
But I'm not going to talk about, but feel free to talk to me about it after. I had to choose. Okay, so my takeaways from seeing this COSY development is that it takes years, if not decades, to go of sustained research and development, right? So this is all NASA funded, but this is multiple years of research and development project funding that has gone through this. The NASA balloon program for us is vital for these iterative improvements. You get it back, you build upon it better, you learn from your mistakes, things do not always go as planned. And proving your science capabilities in the space-like environment convinces NASA to give you hundreds of millions of dollars so you can actually put it into space. Okay, so this is where now I introduce you to the COMPARE project. So the goals of COMPARE, the research and development project at NASA, are to develop the necessary technologies to enable a future large-scale gamma ray mission. So we want to fill that MEV gap, not just make incremental progress above what COSY has done. And we're going to do this by designing, building, and testing prototype instruments through balloon flights. So this project started in 2015, again, kind of following what COSY did. We started with a new technology in about 2015. I graduated from Berkeley working on COSY, and I came over here because I knew this project was just starting off and I wanted to be involved in it. So I started at NASA in 2018. And we started getting hardware on the bench shortly after. We did some initial laboratory tests. We are showing the proof of operation in the laboratory setting. That's much easier than actually showing it on a balloon flight. So we tested a prototype in a relevant environment in 2023. I'll tell you more about what this balloon flight was like. I'll tell you more about what the hardware looks like. And I'll also actually at the end of the talk kind of tell you about where we're going. But we're at the beginning stages of following COSY's path. So I am not lying to myself that we might be 10 or 15 years out from actually getting the selected mission, if ever. But this is kind of, we're here for the long road. But that's effectively what we're trying to do. So I mentioned to you a few slides ago of what a gamma ray telescope looks like. At slightly lower energies, we have Compton scatterings. We have this Compton telescope kind of look. At higher energies, we have this pair telescope. And to fully fill our MEV gap, we need to take advantage of both of these type of detector technologies, or both of these interaction processes. So we build an instrument that can do both. We build an instrument that can be sensitive below 10 MeV by measuring Compton scattering, and we build the same instrument to be sensitive in the pair regime above 10 MeV or so, and we call it the compare telescope, and we shorten it to compare because, or Compton pair telescope, and we shorten it to compare because we're not very clever. And now we have a bit of name recognition. We can never change our name, even though we hate it, but we're stuck with it. Okay, so that's compare. We use the same detector volumes to measure both interaction types, and this single instrument can then span hundreds of keV to hundreds of MeV. If you build it big enough, it can span that whole MEV gap. So this is a CAD model of what that actually looks like. I'll show you the hardware on the next slide, but I just kind of want to introduce you to the detector systems. So we have 4 detector systems that together work to characterize gamma rays. And I'll show you the hardware on the next slide, but effectively at the lower, the first detector system that photons interact with is called our tracker. It's called our tracker because at higher energies, it actually tracks the electron positron particles through the detector medium, as shown on the right here. But it also works as our Compton scattering medium at the lower energies, where a photon can Compton scatter in our tracker material and then be fully absorbed in one of our 2 detector systems that sits beneath it. So beneath that tracker detector, this is made of silicon, I'll show you on the next slide, is our cadmium zinc telluride, or CZT detector system, which is really optimized for our lower energies. It has very good position resolution. And then underneath that is a thick cesium iodide calorimeter. And surrounding all 3 of these is another detector system, which allows us to track charged particles. So in space, our dominant background mechanism is charged particles, which go through our detector system, and they look exactly like particles or photons interacting in our detector because they create very straight lines, and this looks like pair production event. But surrounding our 3 detector systems is this anti-coincidence detector, which is a plastic scintillator, which if there's a charged particle that goes through it, we get a blip. If it's a photon, we see nothing. So it allows us to tag any interaction in our detector systems. If there's an associated blip, we know that those interactions are associated with a charged particle. If there's no blip, then we call that a photon. So this is what we call our anti-coincidence detector system, or our VDO system.
Calorimeter gives you your energy.
The calorimeter gives us our energy at higher energies, yes. So this is looking at the same CAD, but I'm actually going to show you what the hardware looks like now. And beside each of these hardware pictures, I have a face, and this is the graduate student who led that detector system. All of this work is built on the backs of students. So our in the lab, the majority of the work is done by students, not by me, even if I wish I could. But this tracker system was led by Nick Kirshner, who is a GW graduate. He's now actually working at NRL as an NRC fellow. But this is the detector system here. This is a silicon detector that's 10 centimeters by 10 centimeters. And these are the readout electronics to measure the position and energy interaction in one of these silicon detectors. This is our first detector system. Beneath that is our cadmium zinc telluride detector, which is a semiconductor detector, which gives us very precise measurement of any gamma ray interaction. These are the detectors that are kind of stacked in a cube here. We get millimeter precision interaction of the interaction location. And this is led by Lucas Smith, who is weeks away from graduating with his PhD. And then beneath that is actually a subsystem that is led by NRL. So this is the cesium iodide calorimeter. This is actually a scintillator-based calorimeter, very much like what is on Fermi-Lat, but we've done things just a little bit differently. But this is the detector system in an aluminum box right over here. And then finally, the ACD is just a big shiny box, but it's kind of a hat that goes on top of everything. And these are scintillator panels that are contained in each of these panels here. And that was led by Zach Nice. And so this is the detector stack. It just looks like aluminum boxes, but within each one of those aluminum boxes, there's a fancy crystal that is read out with fancy electronics, and then all surrounded by another simulator hat that goes on top. So this took years of effort with lots of other people that I haven't shown on previous pages, but this was a pretty big development effort just to get this detector system all all wired up. And you can see all the cables that go in. This is communication and power to all of our detector systems. So we had what we called an engineering balloon campaign. We are not trying to do any science. We're just trying to show that this works from a balloon flight. The goal was to measure the gamma ray background, so just emission of gamma rays in our atmosphere at float altitudes. And our minimum success criteria for this balloon flight was that everything stayed powered and didn't have any problems. And I'm happy to say that that was a success. So this is our instrument on top of the gondola that flew underneath the giant balloon. So this is the gondola hanging beneath the launch vehicle in the bottom right here. There's that shiny box that sits on top of Compare. And everything else here is kind of supporting electronics. So there's communication systems, there's power distribution, there's even Ethernet switch, there's a flight computer, so there's a little computer that controls everything. This is our team in front of the instrument prior to the launch. And just an example of these degree resolution images that we can make. So this is a source, a radioactive source in the lab that we scan over the field of view of Compare and take images of. So we can show that we can actually measure gamma rays and image them within the field of view. Just to say, we can image. So I did have a video of the balloon launch. We don't need the volume, but you might be stuck with it. Background music. So if you haven't seen one of these before, these are giant balloons, like I said, size of a football field. You can see how large it is once we zoom out, and you see how tiny that crane was, which is, you know, a couple stories tall crane, and Compare is just hanging beneath the crane. So it's only inflated a little bit on the ground because once it actually reaches float altitude, the lower pressures mean that that amount of helium will fill that entire volume of the balloon. So they're waiting for this to slowly lift up until the entire system will be vertical, and then the crane will release the payload and it will float. And actually the edge of the balloon is about right here. So you can see how big this balloon is. This part right here, underneath the edge of the balloon, is the parachute. So the only control we have once it's launched is when to bring it down. There is no steering these balloons. You just get to choose when to pop the balloon. And then the instrument comes down on a large parachute, and it mostly softly touches the ground, and you can go out and pick it up. So we're getting close to when it's releasing. So you can see the crane's actually driving to get, oh, there was the release. The crane's driving to get to the right location. And then it takes about an hour and a half to float up to 130,000 feet is, I think, the flight height that we made it. And there it goes. So we launched from Fort Sumner, New Mexico. We stayed afloat for about 5 hours and landed just south of Albuquerque, New Mexico. Altogether, 5.5 hours for the flight, and we were at our float altitude for 3 hours. We were able to safely recover the instrument. So I didn't go myself, but some folks went out with a truck, were able to bring it back, and we got it back to Goddard, turned everything on. It successfully works again, so that allows us to make those iterative improvements. I'm going to skip this in the interest of time, but just saying we were able to measure gamma rays on board. We were able to measure pair production and Compton events and fine charge particles. So it was a complete success. And I'm also going to skip this because I want to talk about the things that we're working on now. So the balloon flight was a huge success. We showed that it worked in a space-like environment. We measured gamma rays successfully, but we knew there was limitations with the design as we built initially. So we had a fairly small active area, only 10 centimeters by 10 centimeters. I keep telling you these things need to be big, right? So that was a small part of it, or a big part of it, actually. This vertical geometry also was very limited. So if you have a gamma ray scatter in this tracker, half the time it scatters out sideways. It doesn't scatter, straight down. So you want to build something wide as well as deep, but wide. There was also significant passive material. You saw all the aluminum boxes and all that readout electronics. Any photon that interacts in those readout electronics or aluminum boxes, that's lost, right? Like that is not a scientifically useful photon. So that was really limiting. And there was also some challenges with the detector technology, specifically in a tracker, that was limiting us as well. So we had the successful flight, but in 2023, we're thinking about what to do next. So we need to improve the hardware. We need to iteratively design and build to a next big thing. So that's where we have been for the past few years. At the same time that we've been doing the Compare development, at Goddard, we've also been doing some new detector technology development. And that's specifically with these pixel silicon detectors. So this is a technology that the high energy community has been using for particle detectors on the ground. You guys have heard of the ATLAS experiment at the Large Hadron Collider? Have you heard of CERN or the Large Hadron Collider? Okay, so it's a famous, the biggest particle accelerator, I think, still on Earth, I think, or at least it was last time I talked about it, where they bombard very high energy particles, they interact within a very large detector system, and you see exotic matter. This is how they found the Higgs boson, which was a big thing about 10 years back. We're building particle detectors, and we're building particle detectors and putting them into space. What the scientists that are using right now at particle facilities, truly on Earth, is they don't use our old technologies that we flew on Compare 1. They're using these new pixel silicon detectors. And we realize that these are very viable for us to use in space-based astronomy too. I'm going to skip past this a little bit and just talk about our trajectory of this project. So we have taken what was first developed for these particle physics detectors, and we have refined them to make them better for gamma rays. So we don't need super high timing resolution. So they had particles bombarding every like 5 nanoseconds or something like that. Where for us, we have gamma rays interacting every 10 microseconds. So that's 3 orders of magnitude less intense. So we can change some of our requirements and change a few things to make them optimal for gamma rays. And so over the past few years, we've had iterative improvements on these tiny little silicon detectors. So this is about this big for an electronics board, and these are little tiny detectors within them. But the important thing is this scalable. So you don't see this, I mean, I'm telling you, we keep needing to be building big, right? But the power with this technology is we can make very, very large arrays and make this a scalable technology to build something bigger and better. So we were funded in 2023 to build the next version of Compare, which we call Compare 2. We're not very clever with their naming scheme. So this is our first detector system that we flew on the balloon. What we're building now in the lab is Compare 2. And what I want you to see already is that we're using this kind of new pixelated silicon detector technology, and we're making arrays of them, and we're significantly reducing our readout detector, our electronics readout. This is all active detector now. You can't really see the precision here, but these are little 0.5 millimeter pixels on this detector system. And any photon that interacts in one of those 0.5 millimeter pixels, we can measure very precisely. So we went from something with a significant amount of passive material, all this readout electronics is our tracker, to something that is dominated by our active material. So this has significantly reduced the amount of passive material. We've also grown in size. And if you were in the lab with me, I would make you look under a microscope, because this is actually quite impressive when you look at it. But this is 380 detectors together. The resolution quite doesn't do this justice, but each of these detectors is connected to our front-end electronics by tiny little wires. So these are, I think there's 20,000 of these wires on this entire array. This is called wire bonding. So it's bringing these signals from this detector out, sending them along these yellow bus bars. So this is just kept on signaling coming out to our front-end electronics board. So this is how we're getting signals from the detectors out to our front end. But the takeaway here is we've been able to build something bigger. It's scalable. We have much less electronics needed to read out the same detector material. And so this is kind of our upgraded detector system. We've designed this over the past few years. We've fabricated 2 of these. We have them on the bench in Goddard. We've done a lot of carbon fiber structure as well, so to reduce the amount of passive material. And we've done the same with a new calorimeter. This is actually done by our folks at NRL. I was just over there a few weeks ago. We took this photo of the calorimeter, which I haven't spoken too much about. But we're at the beginning stages of building this new technology again, and we're working towards trying to fly this in 3 years' time from a balloon flight from Fort Sumner again. So this is what the gondola will look like. This is actually the cozy gondola. We're just going to repurpose for a flight here. So that would be our detector system, very much like it was in 2023 with the readout electronics, and we would be working towards flying this again. So, the lettering here, I apologize, is a little bit screwed up, but I'm going to revisit this continuum sensitivity plot. I showed you where COSY was and the impact that we were making with COSY. Compare on a balloon won't be better than COSY. It's still stuck in the lower atmosphere. We'd only be observing for something like 30 days, best case, compared to COSY at 20 days, or sorry, at 2 years. But using the Compare-2 technology and building something bigger would take a significant step in actually closing this MEV gap. So this is a mission concept that we developed a few years back that takes the Compare-2 technology, scales it up 40 times tracker layers instead of 10, and 4 towers just instead of 1. So you can kind of see how that scales up. And this is a significant step towards filling the MEV gap. So this is where we're trying to go, but that's not necessarily the end. So I'll leave you with the parting ideas of gamma rays. Hopefully I convinced you are a really unique tool to help us understand the origin of the elements, and Compare is a prototype that we've been developing to try to test these future large-scale gamma ray mission technologies. And after a successful flight, we're now back to the beginning stages of testing new technologies for a more sensitive Compare-2. So thank you very much.
Thank you very much. That was very interesting. We appreciate your time and effort on all of this stuff. I'm sure we, besides my dogs, have some questions. Anybody else have any questions?
How much is it gonna cost?
How much is it going to cost?
Yeah.
So let's see, we have put in at this point 3 separate proposals. So this is all funded through NASA R&D proposals. And each time it gets funded, it's on the order of a few $1 million. That sounds like a lot of money, but I'll tell you the majority of that goes to paying people. So in terms of hardware, this has been less than $1 million in terms of hardware.
That's really not much.
It is not much. It is people's time is the majority of that. Let's see. So I just actually submitted a proposal to do the balloon, to do balloon flight in 2029. And all of our hardware combined, I think, came to $700,000, and that was to build the entire thing. I mean, it sounds like a big chunk of change, but relative to a space mission, I mean, the Roman space telescope that's going to launch just in a month, over $3 billion. So this is pennies relative. And this is just
GSFC was 10.
Yes, exactly. So this is, I mean, again, kind of small scale stuff. This is not Roman. This is small scale stuff in the lab where we're having students build this stuff, but it can be done relatively cheap.
Other questions?
When you get all the data back, you know, it looks like there's tons of data that you get.
There's a lot of data. Yeah.
Right. And you plow through it and you figure out patterns or whatever it is that's in there. Is this leading to any ideas on what the applied science is yet?
Oh, like how to use these detectors outside of astronomy and astrophysics? Or yes. So these similar detectors are used a lot in medical imaging, and then also in nuclear deproliferation. I really struggle with that word, but basically looking for nuclear weapons, things like that. So a lot of our colleagues also work on very similar adjacent non-astronomy related applications. And yeah, the detector systems are very much the same. The technology that you need to image are very much the same. Yeah, there's a lot of connections there.
Is the data transmitted or is it just stored on a hard drive and you pick it up?
For the flight from Fort Sumner, we store it on a hard drive, but from a flight from Wanaka, New Zealand, you transmit it all. And actually recently they're now using the Starlink satellite cluster to do this. So you can fly, they make a maritime satellite for, a maritime dish for Starlink. You can just purchase one of these, I think it's like $20,000 or something like that. You throw it on your balloon and then you have Starlink. It's pretty incredible. Yeah.
Then you get plenty high enough in balloons, you don't need to worry about going to sounding rockets or anything higher?
So we get plenty high enough. The challenge with sounding rockets is you get 5 minutes of data. Do you know how many photons we get in 5 minutes? Not a lot. So you need observations so the brightest gamma ray sources that we could see, we need to stare at them for upwards of 6 hours to get something significant. So we need to be up there for a long time. But the balloon altitudes get us above 99% of the atmosphere for us. So it's pretty significant.
How many? Are you getting terabytes of data in that time frame? Or?
Gigabytes. I think I just calculated this, about 50 gigabytes for a full day, or no, for a full 30 days of flight.
Is it possible to put this in space on a satellite?
That's the intention,
That's
is to
the
eventually
intention.
go to space, but that is not $700,000.
That's maybe more than $1 million.
That we are aiming for a class of mission called a Medium Explorer class mission, which NASA does, that is on the order of $300 million.
Yeah.
If we were to do that, but we have to, I think, go through the steps of proving what this looks like in space. So that's 15 years out probably. But if there's an opportunity, we're going to keep applying for those opportunities, but I don't think we'll get selected until we really show what we can do.
So this may be a very naive question.
That's fine.
But, has there been any discussion about putting a gamma ray telescope on the ISS?
That is not a naive question. People definitely have done it for transient detectors. So
Okay.
people have put gamma ray transient missions on the ISS. And the difference between a transient mission here is when gamma ray burst, for example, or a supernova goes off, you see a burst of gamma rays, and it's very clear. You don't need to image that very well. You just know where it's gone off because it exceeds your background significantly. The challenge with the ISS is it's a very chaotic background environment, and we are so dominated by background photons. The number of photons that actually come from astrophysical sources relative to background environments is on the order of 1% or less. So we have to understand our background environments significantly, really, really precisely before we can do astrophysics. And the ISS is constantly moving around, constantly swinging, things are moving all over the place, and that is unmodelable. So for these types of sensitive observations, the ISS is not a good place, and also is not actually a place to go anymore because it's going to stop operations soon.
We've got a few questions from the remote people.
Yes.
Excuse me. One is some portion of us is hydrogen. So what percent of that has not been in a star?
So all the hydrogen is created in the Big Bang.
Yeah. I think by us.
I knew that answer. I thought that was going in a direction I didn't know.
And then are there no confounding mechanisms for generating those particular frequencies, like some king of black body radiation?
Oh, like, is there any way to get confused about what we're looking at? So that's where I was talking about background emissions are dominant in the gamma regime. So at the balloon altitudes, when we're floating in the upper atmosphere, the majority of gamma rays that we actually measure are from charged particles or cosmic rays interacting in the atmosphere and creating gamma ray showers. So 99% of all the gamma rays that we measure are actually what we call background, so non-astrophysical sources. So there are a ton of mechanisms that create gamma rays that are not the things that we actually care about. And we have to figure out how to filter those out, how to model them out before we can actually observe astrophysically. It's a challenge.
Here's another one. Is a low resolution artifacts because we must reconstruct the image from the glancing incident structure of the telescope?
So the limited angular resolution of Compton scattering is actually due to the fact that, let me see if I can pull. Oh, I can use this from here. So when we calculate the ring here, the ring on the sky, we do that by calculating the Compton scattering angle of this first interaction. And the Compton scattering angle is you can determine based on the energy of the incoming photon and the energy of the photon after the interaction. Those two things can give you this angle. The problem is when you do that calculation, you assume that the electron that the photon scattered with is at rest. You have no knowledge of that electron, right? That electron is buzzing around an atom. You don't know which direction it's going. You don't know if it's going that way or that way. You have to assume that it's at rest. And that is actually the fundamental limit of our imaging capabilities in Compton scattering. Because we don't know what that energy is, we have to assume it's zero. And therefore, we have to calculate this angle without that knowledge. So that it gives us a degree fundamental resolution limit for Compton scattering telescopes.
Our last question, I think it's tongue in cheek, but does it have amp glow?
Does it have amp glow?
It's an imager, and the imagers worry about amp glow all the time.
No, I don't know what that is. So no.
That's a joke.
That's why it's tongue in cheek. Okay.
Yeah, there's a question here in the back.
You said the balloon popped. Do you have a video of that?
I do not have a video of the balloon popping, unfortunately, but it is quite incredible. So what they do is they have a mechanism where they have an explosion that basically does like a ripcord up the balloon that completely opens it in half. And then at the same time, they cut the line between the balloon and the parachute. So they come down separately. So the balloon kind of acts as its own parachute, and then the gondola comes down on its own parachute. They're incredible. You can look them up online because they have been recorded before. So if you look up NASA scientific balloon release mechanism or something, I'm sure you could find something.
Have you smothered anyone's house yet?
We have not. There have been stories of back in the olden days when they were less good at modeling, that there have been, I don't know that a balloon has ever landed on the house, but payloads have landed in property before. But they're much better at modeling that they can get the location down less than a mile, even though it's coming down 130,000 feet. It's very impressive. And they're also much more careful about where they fly and where they bring it down. They only cut down in very unpopulated regions, which is why we fly in these extremely remote locations, such as Antarctica. So that's not usually a consideration for risk.
Okay. So thank you so much, Woody. Any parting words for you?
Yes, thanks again. I'm sorry I'm not there tonight to talk to you more. Actually, when I was at FAA and Director of Data Management, we tracked these things a lot because they would lose parts of them over the years from different places, and we tried to help figure out where they went. You're right, they're better today, but there was a time when they kind of wandered. And there are other people up there as well launching balloons that ask FAA and other people to try to help figure out where they went. But anyway, it's a fascinating area, and a lot of people don't even realize that when they're looking up, see something bouncing around the atmosphere. Balloons are a very good possibility. But
Yeah, no doubt.
A lot of people, NOAA and a bunch of other people launch. But anyway, this is fascinating, good stuff. And there's another world about gamma rays going back to another world. But anyway, there's a lot of stuff out there about it. But we really appreciate you taking the time to talk to us. Again, sorry I'm not going to be able to talk more, but please come out and observe with us sometime or come to one of our other programs since you're at least in the area. But again, thank you very much.
Thank you. It's my pleasure.